I didn't even ask him. Okay. Let's start with my little presentation. My name is Carl Walter. I have my own company, Waltech Systems, but I've been working with Approvecho for almost a decade now. And I do the electronics. All the electronics pieces that you see in the PEMs and the IAPs, those were designed and manufactured by me, the circuit boards. As far as the whole assembly is concerned, I do the IAP meters. Recently I took over the construction of these ones, but the PEMs, as you've probably seen coming and going, those are made by Alex and Michael now up at Stovetech. So today's topics are about the electronics and how they work, and some common problems that not common problems, actually very uncommon problems now that we've learned, but there's some of the problems that we have overcome along the way in this design. The
Carl,
yeah,
is it DAQ or DAQ? Q.
DAQ, yeah, Q. Data acquisition. It's the device that does the digitizing of the analog signals. So let me start out with that. This is just an overview of how the PEMS, the sensor box works, and the same thing applies to the AAP meters. But the DAQ has it has about 24 inputs, but we only use maybe half a dozen of those. And each of the inputs allows for 16-bit conversion. That means that the voltage signal that comes out of each one of these sensors is converted into a digital number from between 1 and 65,000. And there's two ways they can be connected. One is just to run an output from the signal to the input. This is the symbol for an amplifier. And there's an amplifier in there, and then there's actually the analog to digital converter. That's the actual 16-bit gadget. But this is all built into one little tiny chip. And so most of the sensors are just like this. The CO will put out a voltage, and this measures the voltage just like a multimeter would. And then that voltage is converted into a number, and the number goes out through serial communication to the PC. And then the PC does the data logging. In the case of the sensor box, the IAP meter actually has its own onboard data logging. It has a spot for an SD card. So this thing is independent of the computer. Actually, the CO being shown as single-ended is not really the best example. Yeah, you guys took pictures of this and now I'm changing it? Oh well. Okay, we'll do it this way. So this is just the three major sensors that are in the sensor box. And the CO is a little bit different than the other sensors because it doesn't sit at 0. It sits at when there's no CO, the voltage is about 1/3 of the way up the scale. So what you can do is use differential. So this sensor is connected to both the positive and the negative input, and so it only measures the difference between the two inputs, not the amount between there and 0. Ground is 0 in this case. So it does two things. One, if you have something like this CO that has it starts up halfway up its, or a third of the way up its scale, then it automatically subtracts that offset. The other thing it does is it helps with noise, because if noise comes into these lines from the outside world, then if the noise is the same on both lines, it'll be automatically subtracted out. Whereas if noise comes in here, then the noise is just going into the positive, and it's converted into a number just like the rest of the signal. There's no way for this to know that that's noise and not signal from the PM. So there's two advantages of it. This is called differential, and this is called single-ended. And
say it again, please.
this is differential.
Differential, right?
Yeah, and I'd write that on there, but I'm not sure how to spell it. Differential. And this is D, and this is SE. For diff.
So Carl, why couldn't we use the differential for the PM as well?
You can use a differential for anything you want. It requires more wiring.
And the SE is what?
Single-ended. And it kind of depends on whether you have a noise problem. I mean, there's another reason not to use differential, and I'll go into that in a little bit here. Sort of, you start out with single-ended. If you have noise issues or some other issue, then you change to differential because of the other issue that I'll tell you about. And you're actually better off trying to eliminate sources of noise from the outside world than you are to change over to differential. And that's something we learned along the way. It's kind of like, oh, we need more noise reduction, so let's just use differential for everything. Well, then we ran into troubles, and I'll tell you about that. So that's the overview of how the sensor box works.
Carl, the connection between the amplifier B, if I should name it that,
No,
or the CO,
this one.
yeah? That's A and B, that's a B.
Yeah.
Is the CO and the CO2 interchangeable?
Is what again?
Is it possible to?
Yeah, actually, it's all completely configurable. In other words, if you put the sensor box into setup mode, there's a bunch of what they call bit masks, and they're 8-digit numbers, they're 8-bit numbers, and I have a chart, and it allows you to set any channel to differential or single-ended, and you can set the gain. You can set a whole bunch of parameters ahead of time. Most people don't mess around with that because it's preset when we send the thing to you. But occasionally it gets reset because of power glitches or damage or who knows what. So you have to go through and put those numbers in again. But it is completely fully configurable, so any input can pretty much do anything. It's generic to start out with.
So if the signal is only noise, not PM nor CU, which one do you think will give the signal? If an ordinary noise, somebody is speaking behind the background,
What
or
about,
there's a noise, somebody's playing music. which
oh,
one-
you know, this is electrical noise.
Okay,
And
okay.
so this is electrical noise, this would come from,
The cues.
actually, might as well show you on my scope here, you can see the noise. That's why I brought it. Um, oh, I got it completely screwed up. Okay, there's the scope. Alright, so this is, little camera on the scope, and just to show you how much noise you pick up out of this is really the demonstration. Mostly these lights, but the computers and that thing, they all put out electrical noise. And you just become an antenna, and it's hard to see now because it's so much noise. There we go. So see how it just turns into tons of noise that I am an antenna now, and I'm picking up noise from the lights. See, when we get to the light, there's more noise. And so this kind of noise just, it flies through the air, and the closer you are to a source of noise, be it the lights or another piece of electronic equipment, I'll show you that at the end. That's the mother of all noise sources. That's an electric arc. So they're called EMI and RFI. EMI is electrical noise, and RFI is radio frequency noise. And they're not really any, you're seeing both here in this case. It's picking up radio frequency and electrical noise too. So most of the noise we get in this country is from the electrical wiring. And but in other countries we get noise that we can't even test here because I don't know the source. And some of it's from, a lot of it's from the electrical wiring there as well. But they don't have, some countries don't have as much control over radio frequency communication. So there's radio frequency communication and military things like that, that put out bursts and pulse and things like that, that you pick up in any kind of wire. So there's the noise that you see here, it shows up in two ways. The noise can come in between the sensor and the DAQ, and it will show up in your signal. The numbers will jump up and down in ways that aren't what you want to see from the sample. But the other place the noise will show up is here, the serial connection. And this is something that you don't really worry about most of the time. You just plug something into the computer and it works. But we found that in the field, when you just carry the whole thing into another country and set it all up, and the electrical wiring or what have you has a lot more noise than we're used to in this country, that can fail. And what happens is you'll get essentially garbage characters. The numbers will be coming through nice and even, and then you'll get junk. And that is actually been a pretty big problem. And then we came up with a little kit, and I should have brought one of the kits. But there's actually three signals going on here. There's USB here, and then there's RS-232, and then there's just TTL. And the RS-232, easy to read, that's the most noise resistant. So what we've done is we've made the RS-232 the longest wire. So if you want to extend the wire and make your computer farther away from the sensor box, that's the one to make longer. Because this one and this one are more sensitive to the noise that I showed you on the screen before. And the other thing we can do is we can put ferrite beads on here. That's called ferrite. I'll put ferrite like the animal. Yeah, to stop noise there, and there's also optical isolator we can put. Yeah.
The first time we did testing, there was a thermocouple which was coupled with the one that put the meter, which you could see the readings in the digital way. And there was a break which was causing some kind of fluctuation in the reading.
Okay.
Would it affect the circuit?
If you see fluctuation in the reading, it's most likely noise coming in on this side of the DAQ. If you see garbage characters like Q's and X's and things where you expect numbers to be, that's the problem over here. And that's an important thing for you guys to get out of this. If you're setting these things up and you see, and you have a problem with communication, to know that if the numbers, the stream of numbers with the commas, it's something you just see on TeraTerm, where it's the comma separated values that come out every second or so. If those are all numbers and characters, well, a comma, and they look like what you would expect to come out of this, then you're okay on this end. If you see on the graph that the values are going up, or there's spikes in it, or things that are below 0, then there's a problem over on this end. And at this point, these 3 sensors are all inside the sensor box, and the metal panel is grounded. And so these sensors usually don't give you much trouble, but the sensors that are not in the box, the temperature sensor and the flow meter, they have a long wire that goes up to the duct above. So they are an antenna, and they'll tend to pick up noise more than other things.
Yes.
So if you see spikes and negatives that are, the numbers are okay, so the serial connection's all right, but the values, you know, say you're doing your baseline in the beginning and you see strange things going on, the best thing to do is to make sure that the panel, the metal panel in the sensor box, that's grounded to a real ground. An actual earth ground is the best. Sometimes it's a little hard to get, but if you can pound a rod into the ground, moist soil, that's the best ground, and run a wire close to it. And a lot of places don't have ground at all. They'll just be 2-wire. And they may have terminals that have 3, but the third one may be connected to nothing too. And that used to be the case here, but a lot of the wiring got fixed, so now it's not a very good test case anymore. So grounding the panel is important, and there's a green terminal on there for that purpose. And then grounding the metal ductwork too, so that any noise that comes in, the duct is a big antenna, any noise that comes in from there will be conducted to the ground instead of running through the sensors.
But if there is already grounded in the earth, do you still need it?
If you have a good ground in the wall, then you probably don't need it. You'll probably be all right. But a lot of times, especially if you're doing some testing in somewhere where there's some industrial operation going on, the ground may be quite a ways away, and there may be people operating motors or welders or some kind of high current equipment that will make that ground fluctuate. So even though it's an earth ground, if the wire is too long between you and where the post is pounded into the ground, and there's other noise sources in between, that ground may not be good enough. So sometimes you'll end up in a situation where you have to have your own ground closer.
Closer, okay.
Yeah.
Well, what about if you are doing the experiment and it's raining? What about lighting? Is it protected?
It's protected in that the input power supply we separated. There's a power supply. And it puts out, there's about 5 voltages that it puts out, because every single one of these sensors has separate voltages. But what we did is we have a wall wart that's hooked up to the mains, and then that just plugs into the power supply. So this thing is protected by a fuse and, generally what happens if you have a lightning strike,
CMB,
it'll destroy this.
MCB, sorry.
But these things are actually inexpensive and we can give you spares. So, we used to keep this in here, and then if there was any kind of pulse, it would destroy this, and then, you'd have to replace the whole power supply. It's a good idea to run with, surge protectors as well, in addition to, if you can, because these are one-shot deal, and the protection inside the surge protector is often one shot as well. So, if your surge protectors get used to absorb a lightning strike, it may still work, but it's not protection anymore. And the same thing is with this. This can absorb a lightning strike, and it may function, but now it doesn't have protection anymore, so the next time there's a strike, it'll just quit. I think we ship a uninterruptible power supply to help prevent the whole thing from shutting down if there is a power outage. And that has all kinds of protection in it as well. So if you have a couple layers, this and the power supply or a surge protector, then you're as safe as you can get. But that has been a problem in the past, is power surges from other electrical sources. If you have a high power motor and you're running it on the same circuit and you power it down, then often that gives a spike in the voltage in the wall that gets absorbed by everything else in the building. And this is one of those things that has been known to absorb that and end up needing replacement. The output, this part of the power supply is not, it goes from 12 volts down to the other lower voltages. And actually there's a 15 volt too, there's a step up as well. But it's, each one of those little power supplies is isolated, and since it's only going from 12 volts, it's been really rugged. It doesn't tend to get damaged. And the other thing is, since it's 12 volt input, you can run it on a battery or any other 12 volt source that gives you at least 2 amps, and then you're all set. So it makes it sort of a universal input.
What's the age? If you're using the battery, what's the age? Age for the battery? 12 volt age.
Oh, the gauge?
Yeah. The amp hour.
Oh, this is 2 amps.
No, I'm asking if you are using a battery.
Oh, if you're using battery?
Yes.
The main source of draw is the fan. And so if you hook the fan up to the battery backup, I think you get, what, 15 or 20 minutes out of it?
Maybe 10, more than 10.
Okay. So,
1060.
and that's, but it's all a fan that's using the power. If you unplug the fan, then, a 5 amp hour battery will last you 5 hours probably, because this is 2 amps peak, and the average draw is a little less than an amp. So, if you separate if you put this on its own battery and you had a 5 amp hour battery, you're going to get about 5 hours or maybe more out of it. If it's running with the fan too, then the fan uses all the power, and you only get like 50
A
minutes.
battery idea. In one of the notes, they were suggesting that in case you are doing any fault work and you need a battery where there's no power supply, you can use the battery.
Yeah.
And in case of any rundown, you can start the engine just to keep the battery
You can,
charged.
if you're using a car, for instance, or a generator, you can charge it anytime you want. This is, you can go to, 17 volts.
17?
Yeah, about 17.
12 to 17.
12 to 17, which is designed so that it could be used on a car charging system, which runs at about that range.
Now, I'm not about it. In the course of the experiment, and you are charging the battery from the engine through the alternator, wouldn't there be any influence of pollution and noise?
There probably will. It's going to be a lot more accurate if you don't run the engine. If you charge before and after.
Solar panel, look at that.
Solar panel, that's perfect. Yeah. It's, if you have to run the engine during the test, you're most likely gonna have more noise.
Yeah.
Um, And it depends on the engine too. A diesel engine has no ignition, so it has less noise. A lot of modern engines, they have the high voltage for the spark is right on top of the spark plug. So there's very little noise that gets out to the rest of the car's electrical system. So those are pretty quiet too. It depends on how much power the alternator is putting out. So if the battery on the car is fully charged and you don't have anything else on, like headlights and what have you, then the alternator is not working very hard and it has a more smooth output. If you let the battery get quite dead, really low, then the alternator will put out its full 100 amps, but it will also make a lot of noise too.
Yeah.
So you can't really prevent that. It's just a matter of having as few loads as possible.
So if you are using the fan, because without the fan you can't do the
Yeah, you
experiment.
can't do the experiment, right?
So what is the amp for the fan?
The fan
rating?
The fan is like 4 or 5 amps, something like that.
4 or 5 amps?
Yeah,
Oh, okay.
because it's 110 volts, so it's
So
getting converted
that is
too.
seven.
Yeah, so it ends up being the major source of power draw. The other thing is that if you use, the main reason that this is useful, the 15 minutes that you get from the uninterruptible power supply is because a lot of times the power goes out, but that gives you time to go and start the generator. And so if you just have a 110 volt generator or 220 generator to run the system, that 15 minutes is enough for you to get it going. Or sometimes somebody else's job. It's just when the power turns off from the city, then 15 minutes later you'll have your own power going again and you can go doing the test.
But is it advisable to use UPS? We can withstand about 1 hour or 2 hours.
You just have to put a bigger battery on. I mean, you can literally take the battery inside the UPS, just has a positive and negative, and you can take that battery out, or leave it there for that matter, and bring out leads and put it to a larger battery. So if you want to be able to do an entire test on just battery power, that would be the way to do it. Because the UPS automatically converts it to 110 volts and can run the fan. And the other thing is just to try it. If you connect the battery to the UPS, or if you connect the battery directly to this, and then want to charge it with a car, simply start the car and let it charge and watch your baseline in the beginning and see how much noise there is. If it's okay, then you can go ahead and run your test with the engine running the whole time. Now you obviously want to keep it reasonably far away, so that if you need 50 feet of wire, you're probably going to want to use 16 or 18 gauge wire or better.
And there will be losses in the line?
There'll be a little bit of losses in the line, but the fan may run a little bit slower, but in most cases that's okay, since we measure the flow. And if you have a high power stove, then you may have problems with low flow. You'll end up having more concentration than the sensors can measure.
So it is vital to advise if the actual battery and then the amp hour that can be used for about 2 hours, since most of the 3 phases takes about 2 hours.
Yeah.
So why don't you make an experiment and see which type of battery rating?
How big a battery would it take?
Yeah, how much would that rate?
It's really big. I mean, plus when you have to run the gravimetric at the same time,
Yeah, the gravimetric is another deal
it's a
entirely.
lot. It's really big.
So I think it's actually not, with the gravimetric involved, it's simply not practical to run straight off a battery. You
Okay.
have to have a power generation source. So in that case, you would need to run a generator or a car engine to make it work. And the UPS, are you hooking
We can't ship the UPS because you can't take them on airplanes. You can't take the battery on the airplane.
Or put it in a
So you have to
container,
get the battery. You have to get the UPS yourself.
or you can put it in a container when shipping.
No,
They
don't
stopped,
allow
they
it.
stopped allowing lead acid batteries being shipped.
Oh, okay.
But it could go on a container, right?
Yeah.
It just can't go on the airplane.
Yeah.
Okay.
No air travel.
Yeah.
Yeah.
No air travel.
It would be a worthwhile experiment to try different cars and different alternators and see how much noise you
Different
can
noise,
baseline.
yeah.
That wouldn't be too hard to do.
No.
But I don't think it's advisable to use a vehicle when you are also doing your experiments.
But a generator, a standalone gasoline generator, That's,
Somewhere.
that would be more practical. And I think we've done that. I mean, in Peru and Mexico, they've been running on generators without even knowing it. I mean, power goes off and then the generator comes on, and the 15 minutes that you get out of this was enough to let it switch over, and it didn't make much effect, because the generator was, that output was fine, and it's filtered through two things anyhow.
A digression, the type of engine, you were comparing a diesel and a petrol engine. Which is which and why?
Diesel engine doesn't have any spark ignition.
Yeah.
So it's, the spark, the electric arc makes a lot of noise. And so having a diesel engine with no spark, it just makes it electrically quieter. It doesn't affect electronics as much as a gasoline engine with high voltage wires that make noise. They're, well, this is a fun experiment. I'll do it right now.
Oh, you brought the.
What?
Okay.
These are electric arc simulators. So this is one of those things that you shouldn't try at home because it's very dangerous.
I've got safety glasses on.
I have my
so
safety
it's
glasses on, yeah, it's okay.
What I mean.
Let's see how much noise it shows on the scope too. So if you hooked up to Wi-Fi, this will turn the Wi-Fi off. So let's see. It'll come back on. You see all the spikes? The really big spikes? That's from that. So there's just the noise out of the air. And there's electric arc.
What's the scale? What's the vertical scale?
It's about 5 volts.
5 volts.
Here's about 10 volts.
10 volts. So does that mean that if it goes over USB, like if USB is like 3 volts or something?
Yeah, see that's the thing. And those spikes actually go much higher than you would see. They're going right off the top of the screen.
Yeah.
Okay.
Is that electrode?
Yeah, this is yeah, no touching. This is an automotive ignition coil from a car,
Yeah.
and this is a dimmer switch
Yeah.
from just
So
for
the
lights.
switch.
And the dimmer switch has a SCR switch in it, so it makes that pulse. And these capacitors charge up during the time that when it's on, and then when it turns off, the capacitors dump through the ignition coil and create an arc. And it happens at 60 hertz. 60 cycles is the mains power, and another country would be 50 hertz.
Is that a sine wave or a square wave? If I did it now.
It's a chopped wave, really. It's it's more like a triangle because the capacitor charges and then it drops off. So it'd be a triangle.
So Carl, so about the USB and the TTL and those voltages, is that pretty accurate? Like the scope is the antenna, and then the USB cable is like you could kind of put that in the scope and it would have.
Yeah. I mean, I was holding on to this. If I was a USB cable, I'd be picking up that noise that you saw.
Yeah.
And the transition. TTL is 5 volts, so this is 5. And then USB is like 3.3. And then this is RS-232.
Hmm.
So this is a 1. When it's high, it's 1, and when it's low, it's 0. So that's how the bits come through the cable. And the TTL, that's what comes out of the DAQ, has 0 and 5 volts as its 1 and 0 status. USB uses 3.3 volts, so its on is 3.3 and its off is 0. And the RS-232 is 12 volts. But not only that, it's 12 volts plus and minus. So when it's at positive 12 volts, it's a 1. When it's at minus 12 volts, it's a 0. Or it's back. It may be backwards from that. I can't remember. But the reason that this is so much more noise immune than these is because, as you saw, the noise coming off the electric arc, if it's higher than 5 volts, then a little spike could come in here like this, that came from noise, and it could be taller than the 5 volts and taller than 3.2 volts. So that looks like a 1, even though it's supposed to be a 0. But that height here is not enough to make the 12 volts think that it's positive. And same with the negative. The difference between the top and the bottom is so great that noise from the outside world, electric arcs, what have you, can't reach those levels. And there's some other systems that are even more noise immune. RS-485 has an even larger differential. But that's why we want to use a longer cable. If you're making things longer, you want to use this and not either of these two for your extension.
But the equipment coming with the RS-232,
What's that?
the equipment is coming with the RS.
It comes to RS-232. Yeah, it's actually, there's a converter. So there's a little short cable that converts from TTL to RS-232, and that's one that we make. And then there's a USB converter, which is there's various brands. Some operating systems work better with one than with other. You can use anything you like. We're shipping with FTDI right now, which seems to be making most people happy on Windows 7. And it works well with Linux as well and Mac. So that conversion there is something that's done with an off-the-shelf device. And if it doesn't work, the one that we send, you can buy one anywhere or use one that you already have that works well and put it in that spot. Because this is standard RS-232, and all the computers are USB. They simply don't make computers with, there's only one available laptop now that has an RS-232 port. They used to be everywhere, but now they're not. Because consumers don't need noise immunity. They're not concerned with that. Or things like printers and cameras and what have you.
So in the drawing, I've not seen any connection linking to the carbon dioxide.
To the what?
The CO2.
Oh, the CO2, yeah. The CO2 is going to be on another input, so I should actually put another input up here. And it's
No, the question I asked is something like that. I think that was asking whether it's
It's included in the box.
It's included in the box.
So now if you want to increase the number of gases you want to analyze or measure.
If you want, there's plenty of extra inputs. So if you wanted to increase the number of gases that you measure, you can add them on to this, and you have to reset the configuration to put that output into your stream of data that comes out. So we give you another column. The issue with that is, well, there's a couple issues. One is that all the sensors require a different voltage. So the PM requires 5 volts, and the CO2 requires 3.3 volts, and the CO requires 3.3 volts, and the flow meter requires 15 volts, and we have something that requires 12 volts. Anyway, they all require different voltages, and every sensor
Flow
that you
meter
have,
15 volts.
the flow meter does.
15 volts.
15 volts, yeah. And there's a step up in here to do that. So, if you connect another sensor, and you just borrow one of the voltages here, so let's see, we have 12, 5, 3, and 15.
Oh, so
3.
you-
So we have all these voltages. If you just hook one sensor up along with another one, they'll often interfere with each other for a couple reasons. One is that these voltages are sized so for the power demands of each of our sensors. So there's not a lot of extra current available. And the other thing is that the CO2. This is an interesting situation because we used to use a CO2 sensor that was had a little light bulb in it, basically. It uses infrared. It's NDIR, which is non-interfering. I can't remember.
Non-dispersive.
Non-dispersive, yeah, yeah. Anyway, it uses a little light bulb to produce the infrared. And it doesn't run it all the time because that little light bulb uses a lot of power. So the way they got the power level down is that there's a microprocessor inside the CO2 sensor. And it switches the source of infrared on and off at about, once a second or so every time it samples. And the element is, and an element like a light bulb element draws a lot of current when you first turn it on because it's cold. And as soon as it warms up, its resistance drops. So once it starts glowing, its power requirements are less. But the problem with that was that it made the power demand was a spike that kind of went like that. Every time, actually even steeper than that, more like that. Every time the CO2 would sample, it would draw like a 1 amp spike. And the thing was rated for 40 milliamps. So if you have a 40 milliamp power supply here and the thing tries to draw 1 amp, it essentially completely overloads the power supply. And the problem with that is that two things happen. One, it can drop the voltage that you're using here. And if that's connected to another sensor, then that sensor will not have enough power. And so it will cause a blip in the other sensor. The other thing it does is that it puts demands on the ground leads. So these are really small voltages that we're looking at. They're the range that this thing measures is 0 to 2.5 volts. And so let's see, 2.5 divided by 65535. That's 3.8 times 10 to the minus 5 volts
Per unit.
per unit. So each unit is really very small. So extremely small changes in signal level will show up in the measured values. Well, what happens is that the CO2 sensor, the one we used to use, is not synchronized with the sampling of this device. So if you're looking at the PM output, and it had 0 with no smoke, it would go along like this, then it would step up a little bit, it would come down again, it would come up again, and this is the baseline. And it was very regular. And these points here were where the CO2 happened to be on at the same time that was sampling. So it was a beat frequency because the CO2 is independent. Its own microprocessor determines the timing of its sampling. And same with this. So when you happen to be lucky and the two were not sampling at the same time, then the PM baseline was what you would expect. And then as soon as the CO2 and the DAQ were overlapping in their timing, you get this upshift. And that was because that that draw was essentially like connecting a large resistor between ground and power. And so it would actually bring the ground lead up. This ground level would go up just slightly, and it would show up on the input of the AEC. Now you can get around that by using differential, but we found a much better way, and that was to use a CO2 sensor that uses an LED as the source of infrared. And it draws the same amount of current when you first turn it on as any other time.
Okay, I have another question. The 3.8 times 10 to the power 5 volt unit.
Yeah.
Unit. How does it affect the scaling? The scaling on the graph?
Well, the scaling on the graph is done entirely after the fact. So the output from the serial port is these units, and then all the scaling is done on the software. So what you see on the screen, there's actually a little I showed them the box that allows you to change the scales. You can put whatever you want, and that's the calibration. So all these pieces of equipment have calibration values.
Oh, okay.
For a little bit of context too, the PM calibration that we use is about 10 micrograms per meter cube per unit that Carl put up there. And
But
then,
there's one which is 3.381 or something.
well, that's the temperature, but then the CO is like 0.03 ppm per unit that Carl put up. So the CO is super sensitive, but just a small change in ADC units will make a big change in PM.
Because the PM is a much smaller signal. Its total output is I don't know, I have to calculate it, but it doesn't even get up to a volt, whereas the CO2 does.
But once these three signals is in relation with oxygen.
The only one that has the CO requires oxygen, the sensor itself.
Yeah.
From the
So
backside.
in this case, if we are doing firing, assuming you have the fan stove and you don't know the amount of oxygen that is being applied or going to the stove, and now you are getting high PM, high carbon monoxide or this thing. How do you know that the amount of oxygen you are applying is not enough for you to apply excessive?
If you're just
Because
concerned,
normally it's supposed to be about 21%, 20.89%.
yeah.
And now, without this indication around, how will you know that, no, I have to increase my oxygen
Well, as far as the combustion is concerned, this is sort of out of my realm of expertise, but when you're thinking about just the combustion, the higher values of CO and PM would indicate that you don't have complete combustion and you need more oxygen. As far as the sensors themselves being shorted, like if this one does require there's some oxygen in the sample for it to have this chemical reaction occur. This is a chemical sensor, the CO, and if it has no oxygen, you'll get a reading that's off. But it doesn't require very much, and in none of these cases would you have a situation where there's zero oxygen. The only time that becomes a problem is when you're using cal gases. The calibration gases, if it doesn't have any oxygen in the calibration gas, then the CO calibration will be inaccurate. So you have to have a calibration gas that includes a little bit of oxygen. But it doesn't have to be anywhere near close to atmospheric oxygen. It just needs to be enough for this chemical reaction to operate. And there is no situation where you're testing a stove where you would have so little oxygen that the CO wouldn't work.
It's also dilution error. So
Yeah,
that
there's so much dilution there that there's no shortage.
Yeah, good.
Yeah.
On the sensor box in the lab,
Mhm.
by physical observation, I see two meters on the board. One is the PM,
Right.
and the other one is supposed to be CO and CO2.
Yeah.
So the two amplifiers are all embedded in the box that contain the CO2 from this circuit.
They're actually separate. The sensors are in the boxes where the air comes through, and that goes to a small box that's underneath the panel. So there's wiring that goes from the bottom of those boxes to the DAQ, which is a small black box underneath the panel.
In the
And
middle, remember I showed you in the middle.
in the case of the CO2, it has its own microprocessor and own controller. So its output is not analog, it's digital. So the ADC actually has digital inputs. Actually, I've configured it so that it has digital inputs. And so the CO2 that we're using now doesn't actually put out an analog value. It puts out a digital value, and then that digital value is simply transferred to the PC. There isn't actually any analog digital conversion going on with the current unit.
Okay.
So this is actually somewhat inaccurate because now that you mention that, it really goes like this. It bypasses, goes out like that. To be more correct. I have the sensors here so you guys can look at them. This is a PM sensor. Let me pass it around. It's this is the laser here, and this mirrored tube is what collects the scattered light and directs it to a sensor that would go right here. This one doesn't have the sensor installed. There's a circuit board that goes on the bottom here, but the sensor goes through this oval hole and sits there right in the opening at the end of the mirrored tube. So the and then the sensor's output, the sensor it has its own amplifier as well. So the PM signal is actually amplified twice, and so the amplified signal from this goes to the amplifier in the DAQ, and then that's converted into a digital value. So you can take a look at that. There's a lid that goes on here too. So you can see how the assembly goes. And even with that lid, the thing is sensitive enough to ambient light that it still needs to be inside a dark enclosure. So that's to give you an idea of the sensitivity. That even with that black baffle, it still will essentially overwhelm it with ambient light if you use it just like he's holding it there. This is the new CO2. It's it has a sensor on one end and an LED on the other, and it's a horseshoe-shaped gold-plated chamber. And so the interaction between the CO2 that goes in these two little tiny holes is detected by the sensor on one of the, I don't know which was which. One's the LED and one's the sensor, and so it goes around this track and bounces across between the walls and interacts with the gas that's in there. And since the LED puts out a wavelength that's the absorption wavelength of carbon dioxide, the carbon dioxide is the thing that will absorb the most. And so it'll show as a drop in signal input. But then this thing has on the backside, has a full microprocessor and a bunch of amplifiers and all kinds of stuff that converts that back into an analog output. And also provides a digital number that we pick up and pass on to the PC. Let me just give that work. And then the other one, this is not actually the whole thing. This is the CO cell. This is a very well used one. It has 3 terminals, and there's another circuit that will make sure that the 2 terminals are at equal value, and it measures how much voltage, how much current is required in the 3rd pin to keep those 2 terminals at the same value. And so this is like it has acid in it and has 3 terminals that are in the acid and some membranes in between. And its closest analogy would be it's an electrochemical cell. So a fuel cell is the most similar thing. But it's not used to produce, even though it does produce its own power, it's not used to produce its own power. It's used to measure its conductivity. And one of the things, this is sort of an aside, but you'll definitely observe it, is that when these aren't used for a while, they start to generate their own power and their own potential. And they need to be run on the balancing circuit for up to an hour if it hasn't been used in 6 months or so, to bring that the self-excitation, essentially, its own potential has to be brought back down to zero, to the zero level by the circuit. And once that's happened, then it will stay that way for, weeks at a time, as long as it's shorted. And the circuit that it's connected to does the shorting, actually the on-off switch does. So, if you have one of these that hasn't been used for a while, and you turn it on, and the CO signal is way high, just wait. If you just wait for an hour, it'll come back down and be nice and even, and should be at the same level that you were expecting when you used it last. But if you're using the thing on a regular basis, that is not an issue, because it takes a while for that potential to develop on its own. Brand new ones usually come shorted, but sometimes they don't, and they'll take up to a day to stabilize, because they've been in storage for, who knows, 6 months or so.
So if you are working with the instrument and handling, accidentally remove one of the cables connecting to the sensors, what will appear, or how will you see? No.
It should be nothing. You should be able to poke around underneath there and not see a lot of changes in the output. That's actually one of the recommended tests. If you're having problems, if the baseline doesn't stay stable, you can do what's called a wiggle test, and it's just that simple. You turn on the PC and you watch the baseline, and you just start poking things, with the end of a pencil. And if you find something that you can move that causes trouble, then you know that there's a connection issue with that wire. So sometimes, especially when things have been shipped by ground and they've been just simply vibrated for 20, 30 hours, in a solder joint, this is your wire, and then the strands come out like this, and then they're soldered to a terminal. The solder will go around the terminal and into the strands, and then usually it'll break right here. So it won't break at the solder joint itself, it'll break just beyond the solder joint. That's the spot that, and if this wire gets vibrated a lot. So sometimes you'll find that that point is actually inside the insulation. So the wire will look connected, but there will actually be a break right here. And so that's the kind of thing you can find out with the wiggle test, because you'll move this wire and it'll break the connection, and you'll see the output change on the PC, and then you know that you need to redo that connection.
But with the temperature sensor, the thermocouple, is it possible to do that in the thermocouple?
Yeah.
If the break is between, it's about, let's say, 100 millimeters from the tip and it's broken, is it possible to cut it? You can use it.
Yeah,
the sensor will have a tip.
The joint between the two metals is what causes the potential. So all you have to do is reconnect the two ends. So if you had the thermocouple, if your thermocouple was originally like this, and you cut it here, you can just bring it together here, and now you have a shorter thermocouple. But that connection should be, it should be made with a spot welder or a welder. It should be made, the connection here should be made with a spot welder or a welder.
Yes.
So if you have oxygen acetylene, just for gas welding metal, that does fine to weld those two ends together. You can actually just wrap them, but it's not all that reliable. But if you're in a pinch and you need to get your test done, just twist the ends together, and that will be good enough to keep you going. But you don't want to have two joints. You don't want to have a joint here and a joint here.
No.
You want to have it so you want to cut it off and make it shorter and have a new joint. And yeah, that's fine. Yes.
So yesterday, we happened to get a chance to see the under of the sensor box where there's lots of soldering. What is the degree of dry joints which cause any problems?
The degree of what?
Dry joints are the points where we have done soldering such that it will affect maybe the performance of the sensor box. What I mean is that if everything is done and the screws have been screwed, the board is screwed into the box,
Mhm.
how often would that problem occur? Or you don't expect anything like that? For about a year during which it is calibrated? and
It's
you don't need
it's more in terms of the travel, the shipping. And, if it stays in one place, I wouldn't expect to see any problems with any of this stuff. But it's when you ship it from one point to another and it sits inside of a truck that's on a rough road. I have a story, I put a motorcycle in the back of a van and I drove from New York to here. And there was a little, the bolt for the seatbelt was touching the panel. And it drilled a hole all the way through the panel, just the vibration. And when I got there, I thought it was just a small thing, wouldn't be any big deal. By the time I got there, there's a hole that big around, all the way through the plastic panel, because of that vibration along the way. So it's pretty easy to underestimate the forces that come from cyclic vibration in travel. If you just put it in one spot and use it all the time in one place, this kind of stuff never shows up. It's not an issue. And the latest version of the sensor box has, all the wires have been shortened, so everything has been brought together into the middle, so there's much less wire. And the wiring is, we do things like, if you have a sensor with, or a jack with 4 wires, and then you solder onto those, you bring all the wires over like this,
belted together.
and then you zip tie the whole thing around here,
Yeah.
so that keeps the vibration away from that critical point that's near the solders. So things like that, and the other thing, if you keep everything close together, then this wire will only go, a few inches before it gets to another terminal like that or something else. But keeping everything short just keeps the forces away from the trouble spots. And, now, like I said, it's been almost a decade I've been doing this stuff, so I've kind of got to the point where I look at these things and I say, that's going to be your problem, you need to do something like this. And so the current version has very few things that are unsupported or have potential for failure. Doesn't mean it won't happen, because, a car is one thing, it's made for passengers, a truck is another entirely. It has much stiffer suspension, it shakes everything a lot harder. So, the wiggle test is something to know.
Is this equipment coming with the circuit diagram?
Yes.
Okay.
Yes? I think so.
It can.
It can, yeah. We have one, so, yeah. I don't see any reason why you
What
can't.
about consumables?
Consumables, that has been a discussion, but the discussion has been more about calibration. But, because the CO cell is in the specifications, it says it's good for a year, and then you should replace it. But that's not actually true. It works just fine after, we had one come back after 5 years, and its output was half, but it was, after recalibration, it was fully accurate. So the CO is not actually a consumable, it's just something that needs to be recalibrated on a regular basis. And we have in the works an idea to keep track of the amount of time that the CO cell has been run, and also keep a track of the amount of CO that it sees. Because if these things are rated for 0 to 1,000 ppm, and if you give them 2,000 ppm, it doesn't necessarily hurt it, but it will change the calibration depending on how long that happened. So this may be something we get some funding for, is to put a counter in the DAQ that will keep track of the CO, the amount of time it's been in there, and any spikes that it's seen. So you'll actually be able to adjust your calibration and be able to run the CO for maybe 2 or 3 times as long without recalibrating it, because the calibration will be adjusted by the counter in the microprocessor in here. I hope we can do that.
Excuse me.
Go ahead, you.
Maybe as I just, I don't know what maybe the feeling of the others, maybe you could have finished what you present to us, and then maybe the questions.
Oh, okay.
Yeah?
Yeah,
What?
we are working through everything I have on my list. It's just that it's not in the order that it was, gonna be done. But, yeah, we probably should go through. You guys all got to look at the parts. You had a question too, though.
Yeah, I think you probably mentioned this before, but what if we have the power supply and the sensor box connected to the power supply and the blower connected to the power supply and the electricity goes? Because that's a problem we have very often down there, and then maybe we have a battery problem and only the blower keeps running, but then the battery goes out. So can we have a battery connected to the sensor box and one different connected to the?
Yeah, absolutely. You can have a battery connected to this. In fact, if you use a uninterruptible power supply for the sensor box with a 5 amp hour battery in it, or something, even less, a couple amp hours, then the sensor box won't turn off for an entire test. And then you can use a separate power source for the blower and the PM. That would be maybe a large battery running off of, and maybe charged by another engine or a separate generator. That's a really good idea because the sensor box is more sensitive to noise, whereas the motors that are running the fan and the pump for the gravimetric system, those aren't, they just need power. They don't really care how noisy it is up to a point. So if you can run those off a separate source, that's a good way to prevent noisy power sources from becoming a problem when there's a power outage. This is what's in the power supply. There's a lot of space here because there used to be the wall power supply used to be included in here, and then we decided to remove it so that it was easily replaceable. But you can take a look at this thing and see all the different voltages and what it takes to power all the separate sensors. All right, so there's two other things. One of them is this. The DAQ is not an off-the-shelf device. It's something that I make. And the reason that we do that is because it uses a type of sampling called delta sigma. I don't know how to make the sigma. That's supposed to be a sigma. And it is more noise resistant because the way it works is it will put a small capacitor, it'll charge across the inputs, actually, across this. And then it will put that to ground, and it will time how long it takes to discharge that capacitor. And the advantage of that is that if during the time that it's charging that small capacitor, which is milliseconds, that there's a spike of some sort, that's noise, that spike will be, might be tall, but it's not very wide. So it doesn't actually add much charge to the capacitor. It essentially just gets absorbed and averaged out. And so if you have a signal that's going on here and you have a tiny spike that's very tall, that will not show up with the delta sigma, which is the capacitor charge time method of measuring. That will be canceled out. If you use successive approximation, which is what you'll typically see in other commercial data loggers like National Instruments and what have you, they sample along the way. So they have a bunch of sample points. And if your sample point happens to hit the spike, then you get the full spike on the output. And so you have to either average or do some other kind of electrical filtering to try to decide whether what you sampled here was noise or not. The delta sigma system doesn't have that problem. So if you decide you want to do more sensor measurement with these low type of signals, this is the recommended type of analog digital conversion to use. The other method is very high speed, so you can digitize things like sound. This is very quick, but these signals don't change on that. They're basically slow moving compared to something like the speed of a sound wave, for instance. So As long as you're not using a signal that has to have extremely high response time, which is sort of nothing environmental, everything takes a little while to change, this is the way to do it because you have this enormous noise immunity because it will prevent spikes from causing a problem.
So is it possible if you are using the instrument to close the box, or you have to open it?
Too close to what?
The sensor box.
The sensor box.
No, because the magnehelic has to be level.
What?
The B-
I mean-
Oh, closed, I see what you're saying, yeah, the magnehelic has to be, the flow meter has to be level. The nature of the way that the sensing works, it has to be, straight up and down.
So when it is open, you are working, sounds will not penetrate into the.
No, because the little boxes that have the sensors in them,
Okay.
they have, they're enclosed as well. And most of the noise is prevented because it's all on a metal panel, and the metal panel will absorb electrical noise, as long as it's grounded before it affects the other signals. Anyway, the type of sampling that this is something that you'll, if you want to set up some other experiments and stuff like that, you buy an off-the-shelf DAQ, you'll find that most of them don't have delta sigma. You have to specifically ask for that, or it's custom, and that's what we ended up doing. The other thing is clamping. Clamping is in the case of the differential voltage, like the CO has, if you have the advantage of being able to eliminate noise that affects both lines. But on the other hand, especially with the CO, if you can have a voltage up to 5 volts, and that'll be, in a single-ended situation, 5 volts would be way overscale, because 2.5 volts is the maximum that can be measured. So if you had 5 volts here, you would end up with just topped out 65,000. But if you do differential, you can have something very close to the maximum, but slightly different. So if this was say 4.99, and this is 4.98, you'd read the difference. The 0.01 would be what you'd read here. So that sounds really nice because obviously you're eliminating any kind of difference. The problem is if this 4.99 becomes 5 volts, then it starts clamping. And what clamping is, there's a diode here that will try to protect this from overvoltage, and that connects to all the inputs. So as soon as one of these inputs goes above 5 volts, all the other inputs will get pulled up. And so if you notice that something's happening to all of your signals at once, that may be because one of the signals is overloading one of the inputs. And when you're using